Hi there, welcome to this Alchemist Chemistry video looking at nucleophilic addition using hydride ions. First thing I'm going to talk about is how we generate these hydride ions in situ using a suitable reducing agent. The reducing agent we choose is sodium borohydride. This reducing agent is strong enough to reduce things like carbonyl groups, but will not be suitable for reducing things like carboxylic acids, which needs a stronger reducing agent, something like lithium aluminium hydride instead. Now let's turn our attention to the mechanism itself. The first thing we expect students to do is to add partial charges to the carbonyl group and also to show that this hydride ion is acting like a nucleophile by donating a pair of electrons from itself to the delta positive carbon here. And that would look like this. So what we can see here is due to the difference in electronegativity between the carbon and the oxygen being more electronegative in nature, it'll be pulling electron density towards itself, creating a delta negative charge on the oxygen and a delta positive charge on the carbon. That delta positive charge is an excellent target for this nucleophile to attack. It donates a pair of electrons from itself towards the delta positive carbon to form a bond. Simultaneously, the increased repulsion of these approaching electrons will push electron density from this pi bond towards the electronegative oxygen. That's what this arrow here is showing, and this bond will break. So a bond is forming between carbon and hydrogen, and simultaneously a bond will break this pi bond in the double bond here, and the electrons are pushed onto this oxygen, and it will make this oxygen here negatively charged. We're now going to look at the next step and see what happens between that negatively charged oxygen and its approaching water molecule, and that would look like this. So what we can see here is the negatively charged oxygen here is donating its pair of electrons to the delta positively charged hydrogen on this polar water molecule. As these electrons approach, it's going to cause repulsion between the hydrogen-oxygen bond here, pushing it towards the electronegative oxygen in this water molecule, shown by the pair of electrons being moved by this curly arrow onto the oxygen, which will therefore cause this bond to break, and what's left over will be an OH minus ion, which is going to appear alongside our final product. And that completes this particular mechanism like so. Now we can also represent this process with a simple equation, which should be appearing now. Right, so the equation we have here is a balanced symbol equation. We can see that the reactant is an aldehyde, specifically ethanol, and it's reacting with the reducing agent. Now the reducing agent is being represented by the square bracket H, because its ability to cause the other species to gain hydrogen atoms across the course of the reduction reaction. And we've made sure there's a 2 in front to balance out the number of hydrogens on the left-hand side and the right-hand side. You can see this molecule here has 6 hydrogens. The aldehyde only had 4, this ethanol only had 4, so we had to put a 2H here to make sure we have a balance of hydrogens left and right. And finally, the product here is an alcohol, a primary alcohol. Specifically, we've made ethanol.
So this is a run through the mechanism using a ketone. First, you place the partial charges on the carbonyl group and show the attack of the nucleophile on the delta positive carbon and the breaking of the pi bond. Next, we'll draw the negative charge and the lone pair on the oxygen, put some partial charges onto the polar water molecule, and then finally we'll show in yellow the lone pair being donated from the oxygen to the hydrogen of the water molecule and the breaking of the HO bond in the water molecule to leave us with the hydroxide ion.
Okay guys, so as before, I'm going to summarize the reaction with a symbol equation. So first of all, the first reactant here you can see is slightly different. This time we have a ketone. The difference being the carbonyl group is in the middle of the chain of carbons rather than terminal as it was with the aldehyde. Again, we've written 2H, the square bracket H representing the reducing agent we've chosen to use, and the 2 to help us balance out the hydrogens on the left-hand side and the right-hand side of the equation. And our product this time is a different kind of alcohol. It's a secondary alcohol with the OH group, the alcohol group, the hydroxyl group in the center of the molecule rather than on the end of the molecule as it was with the primary alcohol. And there you have it guys, 2 different examples of how a hydride ion can nucleophilic attack and add on to a molecule, and therefore fully summarizing a nucleophilic addition mechanism. I hope you found the video useful. Please look out for other videos on the channel which you might find useful in both organic, inorganic and physical chemistry. And it was great talking to you. I look forward to talking to you in the next Alchemist Chemistry video. Take care. Bye for now.